All right, guys, welcome to your Calculus BC class. So today we're going to talk about integration by parts. So in Calculus AB, we noticed how we can use substitution to reverse the chain rule, but now we're going to see how integration by parts, which is what we're doing today, can reverse the product rule. All right, if you remember, the derivative of two functions that are being multiplied together is right here. All right. Now, what we're going to do here is we're going to take the integral of both sides. So again, we're going to integrate both sides. And remember, when I integrate the right side, I can actually split that up into two different equations, where I can integrate each term one at a time. Now, when I integrate the left side, all I'm left with is u times v, right? And I really can't do anything with this, but what I will do is I will rearrange this equation where I'm going to move this side right here. I'm actually going to subtract this side, and I'm going to end up with uv minus the integral of u prime times v dx. And remember, and all of that, since I subtracted that thing that I underlined, is going to be equal to the integral of u times v prime dx. All right, so this is a formula we're going to use. Okay, so that all probably seems pretty vague right now. So we're going to show you a few things that would help you, right? So the formula for integration by parts, the one you definitely need to remember is this, right? Which is what I wrote above. Now, there's some helpful strategies to choose u and v, and I'll show you what that means in a second. But these are actually really important, and they're actually very useful to do what you're supposed to do in this one. So we're going to let the v be the more complicated part of the integrand that can be easily integrated. All right. So, for example, in this one, essentially what we're gonna try to pick is you have those two different types of functions. Okay, so one of them is going to be u and one of them is going to be dv, or v prime for that matter. Now, it says let u be the part of the integrand whose derivative du is simply the function u. All right, but I found this acronym that you used here, and I don't really know what to call it really other than liate. Latte, maybe not. All right, so this actually tells you the order, right? So if any of these come first in that order, if a logarithmic function is there, you're always going to choose that to be u. Now, if for some reason it doesn't work, and you're going to find out pretty quickly if it does or doesn't work, because it'll become more complicated, all right? And again, you probably don't know anything that I'm saying right now until I actually do a few problems, right? If that happens to be the case, if you choose the wrong one to be u and you choose the wrong one to be dv or v prime, then if that doesn't work, then you're just going to reverse that and just switch them, right? You only have two choices. So if one doesn't work, try the other. So here's the idea, all right? So we're going to pick u. If you look at it, right, according to this, we're going to pick the algebraic part first. So we're going to let u be x, okay? And we're going to let v prime be e to the x. Now, what I'm going to do here is to get du, I'm going to have to take the derivative of x, which in this case is going to be 1 dx. And for this part, essentially what I'm doing here is I'm going to integrate, all right? So basically, I'm going to integrate this, and I'm going to go up like that, right? So I'm going to integrate e to the x, which is itself, okay? And I normally don't write that, though. I don't want to write that, but that's essentially what I'm doing. So you take the derivative of u, and you integrate v prime, and then after that, you're going to use exactly that formula that I wrote for you, right? And the formula says that the answer is going to be u times v. Now, u times v happens to be those two. And this is actually how I remember the formula, right? So I always write those two that are side by side together. So I'm going to write x e to the x minus the integral. And to figure out the rest is that you're going to write v and du, or u prime. You're going to write those two together right there. No specific order. So we're going to write e to the x times 1 dx. So in this case, that's just going to be e to the x times 1 dx. And then hopefully by the time you get here, this integral right here should be something that should be relatively easy to solve for. So the antiderivative of e to the x is e to the x plus c. And that's the answer for that one. Okay, so let's go to the next one. So, and this one's a little bit confusing. It doesn't really seem to be that you have two functions. You have natural log of x dx, all right? So remember what is said on there is that we want to choose the logarithmic function first to be u. So we're going to pick that, we're going to pick that to be u. Now in this one, since I don't have anything else, what I can write for v prime is 1, all right? And if I integrate 1, I'm going to get x, okay? Or I can call, by the way, u prime, I can call that dx, if you want to look at it like that. So essentially, when I take the derivative, the natural log of x is 1 over x times 1, don't forget. And in this case, that's all I need, all right? So remember, the formula says u times v, which in this case is those two things right there. So I have u times v, which is going to be x times the natural log of x minus the integral of those two things in the diagonal, which is v and u prime, right? So the integral of x times x times 1 over x dx. And x times 1 over x is going to be 1. So essentially, what I'm trying to integrate is just 1 dx, or just the integral of dx. That's the same thing. So this is going to be equal to x natural log of x minus x plus c. Excuse me for that cough. My dog is apparently choking on something there. My apologies. All right. Okay, so let's go to example 4. So now we're going to do a definite integral. And it's going to work out pretty much the same. All right, first you want to pick, you have two functions right here. You want to pick one to be u and the other one to be dv, or v prime. In this case, we're going to pick x to be u. And again, if you do it wrong, you can just go back and do it. But according to our acronym, right, which I'll write up here, LIATE, the exponential will be the last one you would pick, right? So in this case, we're going to pick the algebraic function, which is x. All right, so v prime is whatever I didn't pick for that. So it's e to the negative x. All right, so now we're going to take the derivative of x, which is 1 dx, or just dx. All right, and we're going to take the antiderivative of e to the e to the negative x, which in this case is going to be negative e to the negative x. Now, in case you're wondering how I remember that, some of you can probably remember, some of you may not remember, but essentially I can do a u substitution, where I can call u negative x and du is going to be negative 1. So I can have the integral of, or because I don't have a negative dx on this one, I can put the negative right there. So essentially I'm trying to integrate this. That's what I'm trying to do. I can use u substitution for that. Okay, so that will be e to the u du, and the integral of that, well, with a negative out here, the antiderivative of e to the u is itself, but since I have a negative, I would end up with that. And then I would replace this u with a negative x. All right, so this is how, I'm just telling you how I knew what the antiderivative of e to the negative x. All right. All right, so moving on with that, I'm going to go ahead and do the formula. All right, so we have, remember, I'm going to do it a few more times so you can remember. I'm going to multiply those two first. So I have x times negative e to the negative x. And we're going to evaluate that between 0 and 4. Minus the integral between 0 and 4 of these two right here. Is e to the negative x times 1. Now, this is a negative right here, but because that's a negative, I can make this a positive instead, okay? And then hopefully, whatever it is that I'm integrating on this side, it should be easy enough for me to take the antiderivative of it. So I'm not going to evaluate this yet, though I could. There's nothing wrong with that. I'm going to go ahead and take the integral of this first, which is just negative e to the negative x. And I'm going to evaluate that between 0 and 4. Okay? So now I'm going to plug in the 4 in all of this equation, and then I'm going to plug in the 0 in that equation, and hopefully I end up with some kind of number. All right. So this would be negative 4e to the negative 4 minus e to the negative 4. And now I'm going to plug in the 0. So if I plug in a 0 here, I would get 0 minus negative 1, or 0 minus 1, excuse me, or e to the 0. And then I'm just going to add like terms at this point. That's the answer for that. Okay, so I apologize ahead of time. This is going to take me a little bit. Obviously, you don't have to listen to all of the notes. You can fast forward. All right, but I do highly encourage you to at least attempt this on your own, because even though it might seem easy, sometimes they can be pretty difficult. All right, so on this one, according to the acronym that I have, remember the natural log always goes first, right? So I'm going to do that first. So the natural log of x, the derivative of that is 1 over x. And then the other part is x cubed. So I'm going to take the antiderivative of x cubed, which is going to be 1/4 x to the 4th power. I keep forgetting to write the dx on here. All right, so I'm going to go ahead and do the formula again. So I have 1/4. So again, remember, I'm going to multiply those two. Minus the antiderivative. Excuse me, I'm supposed to evaluate this between 1 and e. All right, and I'm going to put those two together. So notice that I have a 1/4, which I can put on the outside of the integral. And I can write this as 1 over x times x to the 4th, which is going to be x cubed dx. And then now I can integrate that. As we all know, this is going to be x to the 4th over 4, or 1/4 x to the 4th. And now I can evaluate that between 1 and e. Natural log of e is 1, so this is going to be e to the 4th over 4 minus 1 over 16 e to the 4th minus the natural log of 1 is 0, so the left side is gone, and this other one would be minus a 1 over 16. All right, in order to add these, I need a common denominator. So it's going to give me 4 minus 1, so that's going to be a 3 over 16. e to the fourth on this side, and this is just going to be plus 1 over 16. Okay, so that's the answer for that. All right. So now we're going to do a couple that are a little bit weird, but we can do it. Remember on this one, same thing. Remember part of my acronym says that I can have an, what is that called? I can have an inverse trig function, which is the I. All right, so I'm going to pick that to be U. So our arctangent of x is just the inverse tangent. Now the derivative of that, for that you need a formula that at least so far now we do not have memorized. All right, but if you remember that formula, it says that the derivative with respect to x of the inverse tangent of a function, in this case I'm calling that function u, is 1 over 1 plus u squared times u prime, or du dx, however you want to call it. You can call this u prime, which is the way I'm going to write it here in a minute, plus u squared, same thing, right? So the derivative of this is going to be 1 over 1 plus the function squared, in this case that's x squared, times the derivative of x, which is 1. So times 1, I guess you really don't have to write that if you don't want to. I probably will just go ahead and get rid of it. All right, so now again, if you don't have anything left over, we can just call this 1 dx, if you will, and we're going to integrate that. We're going to end up with x. Now, when I'm going to write the formula again, remember, as u times v, so it's x times the arctangent of x minus the integral of those two, which is going to be x over 1 plus x squared dx. Now, the main problem with this, and just to let you know that this can happen and probably will happen, is that to integrate the right side, I'm going to use u substitution. All right, so I'm going to switch to a different color. So I'm going to call it, instead of calling it u substitution, I'm going to call it w, because we already used u and I don't want to confuse you. Completely different. I'm just going to try to get the integral of this equation on the right. So I'm going to call w 1 plus x squared. So dw, the derivative of w, would be 2x dx. Now, because in that integral, I don't have a 2. I do have an x, but I don't have a 2. I can divide this 2 out and then put the 2 out here. All right, so when I go back and integrate this, I'm going to write this as 1 over w with the 1/2 on the outside and the dw over here. So again, x dx is 1/2 dw, and the 1 plus x squared is completely taken over by w. All right, so the antiderivative of 1 over w would be the natural log of the absolute value of w plus c. All right, so now I'm going to go ahead and rewrite this as x, this is the final answer here, times the arctangent of x minus 1/2 natural log, but instead of w, I'm going to write the original equation that is substituted in, so 1 plus x squared plus c. Okay, and that's the answer for that. All right, so let's look at another one. This one's definitely a little funky. I'm not a big fan of this one. Took me a couple of minutes to figure this one out, but all right. So if you look at this one, right, the exponential should be the last one you pick, but this is going to turn out kind of weird. All right, so there's really nothing I can do. At least trust me, I did try it. It didn't turn out well for me. So what I'm going to do here is every time I have just e to some power, and this power, if it was anything other than that, really anything almost other than that, when I have the Euler's number to an exponential function to the power of, say, a square root number, I'm going to try to use substitution before I even use integration by parts. Okay, so here's what I mean. I'm going to call w the square root of x. and you're going to see why I'm doing this. It may not make sense at first, so just hang in there for a second. So I'm going to square both sides. And then I'm going to take the derivative, right? So I'm going to take the derivative. So this is going to be 2w dw, and this is going to be dx. Okay. All right, so I'm going to go ahead and replace that. So this is actually going to become e to the w, all right? And then dx is 2w. I should have made myself more space here. EW. And then dx is 2w dw. Okay, so kind of ugly, right? So it is at this point that I'm going to use u substitution. Otherwise, I really can't do anything, all right? So let's go ahead and use u substitution for this, where the algebraic function comes first. Exponential goes last, so therefore I'm going to put that one as v prime. I'm going to take the derivative of 2w, which is 2 dw, and the antiderivative of EW would be itself, plus C technically. But all right, so now we're going to use the integration by parts. Remember, we have those two first. So we have 2w EW minus the integral of those two values right there. So we basically have 2 times EW dW. And then now I'm going to integrate. Excuse me, I shouldn't have written that dW. Plus C. And then finally at the very end, I'm going to go ahead and replace all those W's with this original substitution that I had made earlier. And that's the answer for that. All right, let's go ahead and move on to example number 8. So number 8 actually is interesting, to say the least, because sometimes when you do use integration by parts, you can actually use integration by parts a few times before you get the answer, right? So again, we're going to pick the algebraic function to be u, and the other side is going to be the cosine. Now the the derivative of x squared should be 2x dx, and the antiderivative of cosine, if you remember, should be positive sine, right? So I know we haven't dealt very much so far yet with the antiderivatives, but this is honestly crucial that you remember what are the antiderivatives of all trig functions, right? So this is going to be sine of x. Okay. Sorry. So we have u times v. So we have x squared times the sine of x minus the integral of those two right there. So we have sine, well, x sine of x with a 2 on the outside. You can put the 2 on the inside, it wouldn't really matter, but I always like to pull out my constants out of the integral. But the problem is, to take the antiderivative of x sine of x, I'm going to have to do the integration by parts again. Okay, so this part right here is what's causing me trouble. So I'm going to call, well, I'm going to do something that I already said that I wasn't going to do, but I'm actually going to put that 2 on the inside. So otherwise I have to remember to distribute it to the whole thing I'm about to write. So anyway, so 2x, this is going to be sine of x dx. Right, so the derivative of 2x is 2 dx. And the antiderivative of sine is negative cosine. All right, so here we go. All right, so this part right here stays the same. X squared sine of x. Now the whole thing that I circle there, I'm going to write the whole thing that I'm about to write here. So we have 2x times negative cosine. So that's going to be 2x cosine x minus the integral of 2 times the cosine. Like that, by the way. 2 times the cosine of x, but because that's a negative, it's going to make this a positive. All right, so let's go ahead and distribute that negative, and while we do that, let's go ahead and take the antiderivative of that integral. Now the antiderivative cosine is sine again. But remember, with this negative, that's going to make that a negative 2 sine of x. All right. Okay, so we're done with that one. So because of that, right, we do have an alternate method for integrating by parts, all right, and we can use this technique for repeated integration parts if you can see them ahead of time. This actually works really well for expressions that have something like an exponential, like 2 exponentials multiplied together, specifically one that has an e, or an exponential times a trig function. All right, those actually work really well. So you're going to have to simply create 3 columns, all right? D, where you find the derivative of your choice, and U, where you're going to find the let me say it again. You're going to use column D, where you're going to pick one of those functions. So you're going to take the derivative over and over until you get 0, and then you're going to pick the I, which is going to be your choice for U prime, which means you're going to integrate as many times as it takes, where you have the same amount of derivatives as you do integrals. So I'll show you what that means in a second. That might sound confusing here. So the only thing I don't like about this is I actually like, so here's the weird part about it, okay? Because of the way that the integration by parts works, whatever function you get is going to be, you're going to multiply it times, say, positive 1. You're going to multiply this times a negative, that times a positive, multiply this times a negative, and that times a positive, right? So, but the only thing that I have differently is that I don't like to write the signs on the right side. I think that's confusing for me. I like to write them on the left side. So you do however you like them. So here's how that works, all right? So we're going to pick one of these to be the derivative. Now, if I have something that I know when it takes several derivatives is going to go to 0, then I tend to pick that one because that one tends to be easier for me. Once again, I'm just taking a bunch of derivatives until I get to 0. Now, I don't have a choice, and so I picked that one for my letter D, which is actually like, this would be like my U, and this would be like my V prime or DV, however you want to call it. Same thing. Really what I'm doing is I'm just taking I'm using integration by parts. It's the same thing. I'm just using a table to help me do it faster. All right, so e to the 2x. Now to take the antiderivative of e to the 2x, we can use substitution. All right, where u is 2x and du is 2dx. And because I don't need that 2, I'm going to divide that by 2, blah, blah, blah. So this right here will be the same thing as 1/2 e to the u du. So the answer to that is just 1/2 e to the u, which is 1/2 e to the 2x. Now if I take the antiderivative again of e to the 2x and I leave that 1/2 out, I would still get 1/2 e to the 2x. And when I multiply that times the half that I left on the outside, I get 1/4. And if I do it again, then I'm just multiplying. Essentially, all I'm doing is just multiplying the coefficient times a half every time. Now, that's what I meant about doing this enough times until it kind of matches the amount of derivatives you have on the left side. You see what I'm saying? I'm only going to go that far on the antiderivatives because that's as many as I have. So the cool part about using this method is that now I'm going to use the answers that are going to be in my diagonals, like this. So essentially, I'm going to multiply the d and the I, keeping in mind the sign that I have in front of it. Okay, so the first one's going to be positive. That's great. So that's going to be 1/2. Excuse me. My answer is going to be 1/2 x cubed. Guys, sorry, it's my dog. Stop. E to the 2x minus, now I'm saying minus only because that sign is negative, right? So it's minus 3x squared times 1/4 e to the 2x. So this is going to be 3/4 x squared e to the 2x. All right, let's continue on. So we have plus, let's see, 6x times 1/8. That's going to be 3/4. And again, I have to keep up with that sign. So I have 3/4 x e to the 2x. And now finally I have 6 times 1/16, which happens to be 3/8. And now I have to make it a negative because that's negative. So now I have negative 3/8 e to the 2x plus c. Okay. All right, just give me just a second. Let's go on to the next part where we're just going to use the table method again. So hang on just a second. All right, so continuing on with this example 10 right here. So we're going to use the table method again to integrate x squared sine of 4x. So again, remember this thing they don't actually make space here for that you should at least write on here is the signs, right? So remember, we're going to start off with a positive, then a negative, then a positive, then a negative, right? So this is kind of a perfect candidate for this because notice the sign. If you take the derivative or antiderivative of that, you're going to get cosine, and you're going to get sine again if you take the antiderivative again. And it's just going to keep going. It's never going to go down to 0. However, if I pick x squared to be my derivative, right, or u, if you will, all right, where this is u and this is v prime. If I take the derivative of that, I get 2x. If I take the derivative of that, I get 2. The derivative of 2 is 0. All right, so now I'm going to pick sine of 4x to take the antiderivative of that. Now remember, if you want to take the antiderivative of sine of 4x, you can do u substitution. Now, some people, believe it or not, are able to kind of do this in their head. I just happen to not be able to. So du is equal to 4dx. I do not need the 4, so I'm going to divide both sides by 4. So this will be the same thing as writing the integral 1/4 sine of u du. Okay, so the antiderivative of sine is negative cosine. So this would be the same thing as negative 1/4 cosine of u, which in this case u is 4x. All right, so this would be negative 1/4 cosine of 4x. Now, also, if you take the antiderivative of that again, it's going to work out the same way, except for you're going to have a sine. And the antiderivative of sine is, the antiderivative of cosine is sine. But because that's a negative cosine, I'm going to have a negative sine. So again, the antiderivative of cosine is sine. And I'm going to have an extra 1/4. So if I multiply those two, I get 1/16. And the same thing, if I were to use substitution, the antiderivative of sine is negative cosine, which is going to make that a positive cosine of 4x. And I'm going to multiply the coefficient times another 1/4, which is going to make this a 1/64. All right, so again, I want to use the diagonal. Those are going to be my answers. And remember, you have to keep up with that sign, right? So the first answer, or the first part of the answer, is negative 1/4 x squared cosine of 4x. Now we have 2x times a negative 1/16, but because of this negative right here, that's going to make that into a positive 1/8 x sine of 4x. And the last, this last thing I'm going to write, it has a plus right there, so that's not going to affect the sign. 2/64 is going to be 1/32 cosine of 4x plus c. So that's going to be the answer for that. Okay, so now let's go to, there is a chance where you're going to have to do integration by parts on an integral with both equation, whether you pick this or that to be u or du, is going to keep repeating itself, and the derivative is never going to go to zero. And it seems, at first at least, that you're not going to be able to solve something like that because none of the derivatives are going to go to zero. But there is a way to do that. All right. Now you can use integration by parts, like the first, what was it, 8 examples that we made? Let's see. Yeah, like the first 8 examples, very similar to that. You can use the table method. I'm going to use the table method real fast just so I can show you that. And again, remember, both of those methods are basically the same, right? So I don't want you to think that they're completely different. They're not. So let's take a look at this example right here. So I'm going to make a little table for myself. All right, so I'm going to pick d to be e to the x. So especially when you have an exponential function such as e to the x, you want to use this. All right, and the derivative of e to the x is just itself. It never changes, which is unfortunate. All right, now there's a reason I'm only doing 3, and I'll show you why here in a second. So I'm going to take the antiderivative of cosine. And the antiderivative of cosine is sine. And the antiderivative of sine is negative cosine. Now, again, remember, I still have to keep up with those signs, right? Which may change the way I write my answer. Okay, so, excuse me. Notice something that's a little bit weird, right, before I write it. What's weird about this is that this right here, after I took derivatives and took integrals, is basically the same thing as what I have right there. Almost the same thing, except for the sign's different, right, if I multiply them together. So what I'm going to do here is I'm going to say that the integral of e to the x, and let me zoom in here because I don't want to write too small, times cosine of x dx is equal to, so remember what I'm going to do, right? I'm going to do diagonal normally. All right, so I have hold on just a second. I think I have the wrong sign. Plus, minus. Oh, yeah, never mind. That's going to be a positive. Yeah, notice that this negative right here is going to make this diagonal positive. So we have plus e to the x cosine of x. Now, the weird part is that if I keep doing this, it's not going to give me the answer, right? It doesn't matter. So what I can do, notice that because this is the same, instead of going diagonally, I'm just going to write this as the integral because I don't know what that is. So I need to write that as an integral, okay? So I basically went this way, And then at the end, I kind of reverse course, right? And I'm actually gonna put a video here with the Google Classroom, and I actually found a video where the guy doesn't really use the table; he just keeps using integration by parts until he gets basically the same thing that I got. Okay, so now I'm gonna have minus. I'm gonna write that in a different color so you can see what it is that I'm doing here. Now, remember that minus came from this little formula right here. I have e to the x minus cosine, right? So I have e to the x times a negative cosine, I should say. So that's where this sign came from. Okay, but notice that right there is exactly the same as this. All right, so what I can do is I can add this to the left side, which is what I'm going to do now. And I'm just going to rewrite the rest. And then finally, what I'm saying is if I divide this by 2, then I have my answer, right? Because now I have the integral of e to the x times cosine of x dx is equal to this. Well, I guess I should write plus c. So I'm going to divide all of this. So the answer is going to be 1/2. So that one's kind of a crazy tricky one, right? So again, I will attach a video of that. If that didn't make a whole lot of sense to you, I did find a video where a guy does a problem sort of like this, right? But what I have noticed is that I'm only going to use this when both functions that are in the integral are something that are going to basically never going to go to 0 if you take a derivative. They're just like sines or cosines come to mind. E to the x, for example, those are the only things that I can think of. Just keep the derivatives or antiderivatives of them basically keep going in almost like a reciprocal manner. I don't know if that's the right term to use for that, but I'm not going to do example number 12. I can set out the completed notes for you so you can see them, but just for the sake of time, hopefully that one doesn't seem actually too bad, but for the sake of time, I'm not going to do that. Okay, so hopefully you understand this, but let's just go ahead and work on that homework. Remember, there's no way to understand this without doing the homework, so let's work on that homework. And if you got questions, I'll answer them when I see you.